Today's lesson is on soil porosity. We're going to be taking a look at how to calculate it as well as how to define it. First, to understand its definition, we first of all have to understand what particle size has to do with porosity. As we've already talked about, there are three different soil sizes or soil textures. One is sand, which tends to be larger. The other one is silt, kind of medium in size. And of course, the smallest is clay. To give you a perspective of how they look in comparison to each other, let's take a look at this chart. In this chart, you'll notice that it gives us a relative size of these particular particles, going from gravel, which obviously is the largest, to the very smallest component, that being clay. It's microscopic in comparison to, of course, gravel and sand and silt. Depending on how those particular parts or particles kind of come together in the soil will determine its porosity. Let's take a look at our lab that we did a few days ago so you get a sense of the comparison between gravel and sand and how that impacts the actual soil porosity. But before we do that, again, I just wanted to kind of point out what is important in terms of when we're measuring porosity. If you take a look at this picture right here, all of this empty space right here are what we call pore space. And that pore space is real crucial in determining porosity because that's the thing we're actually measuring. So if we were to come up with any kind of definition, it's just a measure of the amount of pores in a given soil matrix, some certain volume, whether it be, for instance, 166 milliliters like in a 9-ounce cup, or like in our lab today we had a 4.5 ounce cup, which is 133 milliliters. So that's kind of an important number to remember as we do the calculations. But anyway, in this particular diagram of a well-sorted gravel, you can see there's lots of pore spaces, and they're big and they're open, and water's going to be able to fill those fairly easily. Whereas here on the other hand, you have sand kind of filling up some of these pore spaces instead of water. So you'd probably think this one is going to have a lower porosity than this one, which may have a higher porosity. And for the most part, in this particular picture, that holds true, but not in every situation. That's why it's important to understand what is porosity and what kind of soil particles are we talking about. So let's take a look at our lab and try to get what we're really trying to measure. The lab I'd like to show you today is the one on porosity. As you can see there, each cup is labeled, and the cup on the left is sand and gravel. As we examine it, you can see the gravel is mixed out throughout the matrix, and that's in the 9-ounce cup. We fill it about halfway. While the other cup, of course, is a 1/4-inch pea gravel, and you get a good look at that. It's just gravel. There's maybe a few pieces of or parts of sand. For the most part, it's pretty much gravel. Now, what we're going to be doing with those two cups is we're going to try to calculate their porosity. And the way we do that is using water. And we're going to be taking the 100 ml graduated cylinder, fill it with 100 ml of water, and we're going to pour it in each one of them. Start with the gravel. As you can see, as I'm pouring it in there, I'm careful to make sure that we have all of the voids or pore space filled up right to the very top. And right to the very top is really important, and we're going to check that out to make sure we've covered all of the pebbles or all of the gravel up to the top. Make sure all the voids are filled up, so all the pore space in that cup is taken care of. Also, if you take a look, you look at the graduated cylinder, and you can see there are basically 33 mLs of water still left in the graduated cylinder. We'll do the calculations later. So you can see for the gravel and sand, same kind of thing. I'm going to take the graduated cylinder and I'm going to pour as much as I can into it until it's all saturated with the water. And on this one, it's a little trickier because I want to make sure all of the pore spaces are filled in the soil matrix. I want to make sure it goes all the way through it, and you can see I'm checking for any dry spots in the cup to make sure that the water is filled in all those pore spaces. I'm going to give it just a few seconds here to make sure that it's gone all the way to the bottom. So I'm going to check the bottom. You see a couple of dry areas, but for the most part, it's been filled up. And when we look at the graduated cylinder, we should be able to see that there are approximately, let's see here, it looks like 50, yeah, there we go. 57, I believe 57 mLs are left in the graduated cylinder. So there you have the experiment. We just wanted to make sure that each one was filled up with the appropriate amount of gravel, and then we'll do the calculations. You can see as I examine that, it's all filled right to the top. And I'm just going to check one more time. There we go. I've got it in the right place. Make sure that we don't have any voids not filled up. So I check it one last time, and there you have it. In just a moment, we'll go to the second part of this presentation and look at the calculations to see really what is porosity. All right, now that you've seen the lab, at least an example of the lab, and many of you probably had similar types of numbers, but what do all those numbers mean, and how do we use those numbers to actually do the calculation? Now remember, what we're really measuring is the amount of pore space or airspace that's left in between the soil particles. So one of the ways we did that is put water in it so it would fill up all of those pore spaces, so that then we can measure approximately how much volume of water it would hold, so that we can kind of compare what, like for instance, how much soil was in that cup, how much was filled up with air, so we come up with a percentage of pores that's in that particular soil separate. So let's go ahead and do the analysis. We're going to start with gravel. Now on gravel, and this may be a little bit confusing, but when we poured it, you remember we had 33 mLs left in the graduated cylinder. So we want to know really how much water went into the gravel or stayed in the gravel in the pore space. So we take 100 mLs and we subtract 67, excuse me, actually this should be 33, sorry about that, so that we would have 67 mLs in the gravel pores, which means if we take the 67 and divide it by 133, which is the total volume of the gravel in the 4.5 ounce cup, because that converts to mLs, that means 50% of our cup had pore space. So the porosity number would be 50%. So in terms of the amount of space that can hold water would be 50%. So let's take a look at our next one, which of course is sand and gravel. And that's important because this one is very well sorted. The gravel is really well sorted. It's a 1/4 inch pea gravel, as I said. So it has it's very consistent in the quality of the aggregate. Now let's take a look. That is something that isn't a very consistent, and that would of course be the sand and gravel, because they're two different particle sizes. So again, just like in the other one before, we had 57 left in the graduated cylinder. So we subtract 100 from 47, so we know how much was actually in the gravel pores. And when we did our calculation, 43 divided by 133, we get 32%. So 32% was space, was a pore space, which means, if we take a look over here, that gravel had a much larger pore space. So because of that, it's able to hold more water in it. So if you're looking for an aquifer, maybe this particular gravel component would be much more filled, if you will, with water. And so that might make a really good aquifer. On the other hand, we have this sand and gravel. It held a little less, 32%. Maybe not as full, not as rich with water, but still is able to hold water. Now,
if you take a look at the standard chart I have over here, you'll notice that gravel, in this sense, is much higher than this one. Primarily because this one was very well sorted. If we were to dig down to an aquifer, you're not going to get this nice, pretty quarter-inch pea gravel all throughout. It's going to have different shapes and sizes. So that's why it's much more coarse and be 20% probably. Whereas the sand and gravel, because it is not well sorted, it has different sizes. Some of that sand would fill some of the gravel pores, so it would take up some of the space that would normally have air in it. Now it has sand in it, so it will hold less. So really, when you take a look at it from that perspective, porosity is a great predictor in terms of how much water a particular aquifer can hold. It's also going to tell us a little bit about permeability, and we'll talk about that in the next video. I hope this has helped you. And remember, when we're talking about porosity, it's really all about the space. All right, we'll see you later. Thanks.